time. Most of us live by the clock. Whenever we measure how long it takes to get from one place to another, or how long it takes for something to happen, we measure rates. Rates measure the pace of our lives and our technology. Probably the most fundamental rate we experience is the turning of the Earth. When we say that the Earth makes one revolution per day, that is its rate of movement.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Technology must operate at specific rates. If events take place too quickly or too late, the job cannot be done properly. So measuring rate is important. Rate is a measurement of what happens and how long it takes to happen. In a mechanical system, objects are moved from one place to another over a period of time. A mechanical rate is the distance the object moves, or how far over time. How far might be feet, miles, or kilometers. The time could be seconds or hours. So feet per second or kilometers per hour are mechanical rates. A mechanical rate can also measure an event and how often it happens in a period of time. This machine makes 48 milk containers per minute. That's the productivity rate, the rate at which this mechanical system operates. A fluid rate measures how much is moved in a period of time. How quickly these firefighters can put out the fire depends in part on the volume of water that moves through the hoses during the time they're fighting the fire. This fluid rate might be measured in gallons per minute or liters per second. An electrical rate is also a measurement of how much moves in a period of time. How much is the amount of electrical charge, or coulombs, that move through a circuit every second. Look closely at the meter on the side of a building. The rate at which the wheel inside the meter turns indicates the rate at which electrical charge is moving through the circuits in the building. How much is also important in thermal systems. How much heat energy moves from one place to another in a period of time. Rate. It measures how far, how often, or how much over time. How much fluid? How much electric charge? How much heat energy moves in a given period? Usually, a technological system has many different types of rate in operation at the same time. A power dam, for example, operates on fluid rates, mechanical rates, electrical and thermal rates. They all work together and they all affect each other. John Miller is an operator. His job is to make sure that the interaction of all these rates is precisely controlled.
The first rate we'll discuss is the fluid rate. By controlling the gate position, we can control the rate at which water flows through the turbine. Right now we're at about 42% of gate opening. That will equate to about 2,400 cubic feet per second of water flow. That in turn will drive the rotating mass of the generator at a speed or a rate of 150 RPM. Those two factors combined will give us an output or an electrical rate of approximately 37 megawatts or 37 million watts. As a result of this transfer of energy, we have a thermal rate of heating in the various bearings in the generator. We apply cooling water to them to dissipate that heat. We've got a drawing right over here that'll show you that. Water enters the hydroelectric unit through this passage here called a scroll case. It flows then through these wicket gates, which control the rate of flow of water onto this turbine, which converts the hydraulic horsepower into mechanical horsepower here. As this turbine rotates, it drives the rest of the generating machine through this connected steel shaft here that goes up to the generator itself. The rate of heat exchange caused by all these conversions is controlled by the amount of water flowing through these coolers here, which are used to dissipate that heat.
Now that you've looked at rate in a number of different ways, let's start over and see if you can spot mechanical, fluid, electrical rates in this little scene.
Good morning.
You're late.
Yeah, I know.
You have just seen many different examples of rate. Now let's see how many you found. The clock itself is a mechanical system, but it's actually based on the rate at which the Earth turns.
Oh, man.
This one's a little tricky because he's controlling the rate of heat flow from the water heater. This one's obvious. If you said thermal rate for the toaster, you were right, but it's also electrical, as was the coffee pot. In fact, all electrical appliances depend on a steady flow of electricity from the household circuit. This one's easy. Revolutions per minute is a mechanical rate. In addition, the movement of the car as a whole is a mechanical rate. We move fluids from place to place at specific rates, but with this fluid, we pump it in at one rate and we burn it at another rate, which affects our gas mileage.
Good morning.
You're late.
Yeah, I know.
How far something moves over time. How often something happens over time. Or how much of something moves over time are rates. Controlling rate is controlling the very pulse of our technology. By the way, did you wonder why our hero was late getting to work? Sometimes, if rate is not carefully controlled, somebody has to pay the consequences.
Car registered in your name?
Yeah.
81 Mazda. Okay, signature down here.
It's just been one of those days, you know, nothing is going right. I'm running late to work. Spilled my coffee.
Which car wins the race? The one which travels at the fastest rate. In mechanical systems, rate measures an event and how long it takes for that event to happen. These machines are making milk containers at a specific rate. The number of containers that come out in the end is the production rate of the entire factory. How fast the factory produces bottles will determine the rate at which the money rolls in when the bottles are sold. Rate is an event over time. Sometimes an event can be a motion, when an object covers a distance. For example, these cars are moving along the assembly line at a certain speed. Speed is a rate, a distance over elapsed time. Take, for example, a speed limit. The sign tells you a unit of distance and a unit of time. That's how you find rate in a mechanical system, distance divided by time. So for miles per hour, miles is the unit of distance, and the hour is a unit of time. Kilometers per hour is also distance over time. It's this relationship between distance and time that the police use when they catch speeders from the air. There are markings on the highway that are spaced at specific distances. A helicopter alerts a police cruiser who may also be using his radar detector. It works in a similar way, by electronically measuring the time it takes a vehicle to cover a distance and calculate the speed. If you get caught, your rate was too fast. Sometimes there's more than one rate to keep track of at the same time. The pilot of this Harrier jump jet has to be concerned with his speed forward, but also his speed downward, his rate of descent. Whether the units are feet per second, kilometers per hour, or centimeters per year, they are always distance over time. A technological device does not always move at the same speed. In other words, its rate will change. Watch what happens as this aircraft speeds up for takeoff. The dots mark off equal units of time. Compare that to when the same aircraft flies by. And compare that to a landing. The dots mark off equal units of time. When it took off, it covered a greater distance for each unit of time. That's an acceleration. Flying by, it covered the same distance per unit of time, a constant rate. And landing, it covered less distance, a deceleration. Speeding up, slowing down, starting, stopping, in fact, any change of motion is an acceleration. Suppose you want to calculate an acceleration. What you are measuring is how much the rate changes over a period of time. So what you need to know is the difference between the speed at the beginning and the end of the change. So take the speed at the end of the acceleration, or the final speed, and subtract from that the speed you began with, or the initial speed. Divide all of that by elapsed time. What you end up with is a rate over time. You could call this one meters per second, but usually an acceleration is expressed as meters per second squared. So far, we've only been talking about linear systems, systems that move in a straight line. In rotational systems, the rate can also be constant or changing. The calculations for rate in a rotational system are similar, that is, displacement over elapsed time, except that displacement is measured as an angle of rotation, represented by the symbol theta.
531, 681.
Here's an excellent example of rate being carefully controlled.
Production on engine 2307, come in the inbound at Archer train in R5, over.
This is the Norfolk Southern Corporation shunting yard, where trains are assembled using gravity. Can you see how it's done? These boxcars are not powered. They're coasting to their destinations because of a precise control of rate. When a car is pushed to the top of the hill, a computer weighs it and calculates the speed the car needs to coast to its destination. As the car rolls down the hill, it accelerates. Brakes in the track, also controlled by the computer, only allow the car to accelerate up to a calculated speed. The car then coasts the rest of the way on its own, decelerating until it reaches the train with just enough speed left over to couple up. Rate in a mechanical system is speed. A changing rate is an acceleration. Controlling rate makes sure that objects are moved just the right distance in just the right time. Moving fluids. Nature does it with rivers and streams. We do it with pipes and pumps. Whether we're moving a little or a lot of fluid, we need to know how much is being moved and how long it takes to move it. This is rate in a fluid system. Unlike mechanical systems, fluid rate is not concerned with how fast the fluid moves. The water is coming out of these two hoses at the same speed, but because one hose is bigger than the other, more water is coming out of the larger one over the same period of time. So, although their speeds are the same, the larger hose has a larger fluid rate. In fluid systems, the important factor is how much fluid moves over a period of time.
By controlling the
Recall
gate
that
position,
John Miller controlled the fluid
we
rate of the
control
water passing
rate
through
at
the
which water
dam.
flows through the turbine.
By opening and closing the
Right now, we're
gates,
about
he
40%
controlled how
gate
much
opening,
water passed over the
all the way to about
turbines,
2,400
and therefore
feet per
how
second.
much electricity the dam generated. How much in a fluid system can be measured in two ways. The first is to measure volume. Volume over elapsed time is a fluid rate. It can be expressed in gallons per hour, liters per minute, or cubic feet per second. In each case, it's a unit of volume over a unit of time. The second way to measure how much in a fluid system is to measure the mass of a fluid that moves over a period of time. A pilot is not as concerned about the number of gallons of fuel he takes on as he is with the weight of the fuel, because that affects the performance of the aircraft. So in this case, the fuel flow rate is measured in pounds per hour, or kilograms per minute. These two ways of measuring fluid rate, volume over time and mass over time, simply measure how much fluid moves in a given period. The next time you fill up, you can calculate the flow rate of a pump. The pump tells you the volume. A watch will tell you the time. Controlling rate in a fluid system is important because other rates often depend on it. The rate at which the water flows through the dam determines the rate at which it produces electricity. When fire pumpers are using their internal tanks, flow rate determines how long the supply will last. Flight engineers calculate the range of an aircraft based on the rate the fuel is burned in the engines. Usually, rate is controlled by a technician, but not always. In a dairy farm, the fluid rates are all determined by the cows. Fortunately, they usually cooperate.
Believe it or not, if you have nothing more than a stick, a tape measure, and a stopwatch, you can measure the flow rate of that dam. The first thing you've got to do is determine the average depth of the water. You can do that directly like this. So this water's about this deep. Next you need to know the width and the length. You measure the width directly. The length, you don't measure the whole length of the river. What you do is measure a volume of water that moves over time. That's where you use the stick. So take the stick and throw it into the fastest part of the water like this. Then mark where the stick lands and see how far the stick moves in a period of time. Now you have a length, a width, and a depth. This is a volume of water that moved over that period of time. Volume over time is the flow rate. In other words, the flow rate of a fluid system is how much fluid moved over elapsed time.
Bob, check that depth again.
Again? 1.6.
Again.
1.62.
Again.
1.61.
One more time.
I'm gonna get you for this.
Another program has crashed. Why? Because the amount of electricity flowing into the computer suddenly changed. For companies that depend on large computers, such an event could be very expensive. So the power lines to the computers are usually protected by devices that control the flow of electric current through the sensitive circuits. In other words, they control the rate in electrical systems. Like the flow rate of a fluid, electrical rate is a measure of how much flows past a point in a given time. But instead of measuring the amount of fluid that flows through a hose, you measure the amount of electric charge that flows through a circuit in a period of time. The unit of electric charge is a coulomb. Electrical rate is 1 coulomb flowing past a point in 1 second. You'll recall that the number of electrons in a coulomb of charge is about the same as the number of grains of sand in a dump truck. Fortunately, the unit of electrical rate, the ampere, lets you count dump trucks instead of counting grains of sand. The ampere is exactly 1 coulomb per second. This makes it very convenient to measure electrical rate because the ampere is a rate. Unfortunately, the formula for electrical rate is not so convenient because the letters don't match the words. I is the rate in amperes, Q is the charge in coulombs, and T is the time. Most precision machines usually run on electricity, so controlling electrical rate is important. The current on these arc welders has to be maintained at 500 amps so they'll create enough heat to make the weld. For arc welders, heat is useful, but very often heat is the enemy of electrical devices. Anytime electricity flows through a wire, it generates some heat. The more electric current, or the higher the electric rate, the more heat is produced. So all wires have to be rated according to the amount of current they can carry. Large wires can handle more current than smaller ones. That's why no device should carry more current than it's rated for. In fact, the sole purpose of a circuit panel is to limit the rate of electricity in a building. If the wires begin to heat up from too much current, the breaker trips. Even the breaker itself operates by heat. As the rate of electric current increases, a bimetallic strip inside the breaker heats up and bends. The higher the rate, the more heat and the more bending. Finally, it reaches a point where the flow of electricity is cut off altogether. Even when a device has been designed with wires properly sized to handle the current, some heat is still generated, and it can build up over time and still cause problems. A good example of electrical rate being carefully controlled is a diesel locomotive. Although we call them diesels, the motors that drive the wheels are actually electric. The diesel engine is just used to run a generator that makes the electricity for the motors that drive the wheels. Trains that are all electric get their power from overhead wires, a third rail, or in the case of this monorail, from a power track located here. In any case, when the engineer opens the throttle, he's controlling the rate at which electric charge is delivered to the motors. Controlling that electrical rate is particularly important during startup. If the charge is delivered too quickly, the motors could be overloaded, therefore overheated and damaged. That rate of flow of electric charge to the motors affects the mechanical rate of the entire train, its speed. You'll recall from the work unit that Lee Klaus is constantly concerned about the lifetime of his batteries in his electric car. This is directly related to the rate at which he draws the current out of them to run the motors. To make the batteries run a little longer, he uses a device that helps him control that rate.
This is a battery-operated electric car. This is an electronic controller. The reason I like this particular controller is because it works like an electronic switch, which turns the power from the batteries on and off very rapidly or very slowly, depending on how fast I want to go and how quickly I want to use up the amperage in the batteries. It is an electronic switch. It does basically the same thing as a mechanical switch. It opens and closes rapidly or more slowly as I accelerate. If I'm moving along slowly, maybe the switch is opening or closing 50% of the time. So in effect, the batteries are off 50% of the time. So the reason I like this electronic controller is that it allows me to extend my range by, in effect, turning the batteries off part of the time.
As Lee Klaus saves energy with style, he's actually controlling the time element of the rate formula. How much charge is limited by his batteries, but his switch breaks time into little pieces so he can coast the rest of the way. Power companies must also be constantly aware of rate, because the demand is constantly changing. Every night around supper time, most people are using their electric stoves, fry pans, blenders, lights, and televisions. These are called the peak hours. The electric utilities must generate more electricity to meet that demand. If an electrical rate is not carefully controlled where it's generated and where it's used, someone could be left in the dark. The home team is hot, the crowd is hot, and the temperature inside the dome is rising. Trying to maintain a comfortable temperature inside the huge space of a dome stadium is an enormous task, one which involves controlling the rate in which heat circulates. Controlling rate in a thermal system is similar to a fluid and an electrical system. What counts is how much moves in a period of time. The how much in a thermal system is heat energy. So rate in a thermal system, or heat flow rate, is the amount of heat energy moved in a period of time. That's H over T, which could be calories per second. Measuring the flow of heat is vital to the operation of many pieces of equipment. Of course, furnaces and boilers have to generate heat, but equally important is the removal of heat from a system. For example, a car engine generates heat as it burns the gases in the cylinders, otherwise it doesn't run. But if that heat is not taken away by the cooling system, it builds up, the engine overheats. So the cooling system in a car uses a thermostat to control the heat flow through the engine so that the amount of heat flowing into the engine is balanced by the amount of heat flowing out. The same is true for a dome stadium. Heat is generated by an unusual source. Mary Prohaska is a technician who must adjust the air conditioning system so it'll take the heat away at the proper rate.
This is the central control panel for the Tacoma Dome. We have a total energy management system inside the dome. We, in effect, generate our own weather. Its major contributing factors are the people, the amount of people that we have in here, and what they're doing, and the event that's going on. If we have a great deal of people moving around, say during a concert or some other kind of active event, they're going to generate much more heat, and that will affect the way we control our system inside the dome. The air coming back from inside of the dome is read on this gauge. This tells us what we're drawing from the main arena inside of the dome. We mix that with the outside air, and this shows us what we're putting into the dome. Now, if there's a lot of people in it, this gauge will want to read lower than, say, is comfortable, because the people here are going to heat it up to an uncomfortable level. Now, if we can't keep this low enough and if it's cool enough outside, we'll bring in more outside air. Say if we have ice, it's naturally going to be cooler. We'll want it at a cooler temperature. People expect that. If we have a concert, we know that it's going to be much hotter. You've got lights, you've got people crowded together, packed up against the front of the stage, generating a great amount of body heat. We take all this into account when we're adjusting our controls and making these people comfortable.
There are 4 things that affect the way heat energy will move in a thermal system: temperature difference, surface area, thickness, and thermal conductivity. Let's look at the first case. Remember that heat moves from warm areas to cold because of temperature difference. The larger the temperature difference, the faster the heat will move. This is why Mary Prohaska is concerned with the difference in temperature between the people in the stands and the temperature of the air, because that determines how quickly the dome gains or loses its heat. The second factor that affects the flow rate of heat is surface area. In cooling systems, radiators are usually used to take away the heat. But a radiator is simply a large surface area exposed to the air. The reason there are so many tubes and fins in a rad is to expose as much of the surface to the air as possible, so more air can come in contact with the material to be cooled. This is also why air-cooled engines have fins, to increase the surface area of the hot metal so the air can remove the heat as quickly as the engine generates it. The next factor in heat flow is the thickness of the material. Since heat energy can flow through solid objects, the thickness determines how far the heat has to travel. So the heat will move more quickly through a thin material rather than the thicker part of the same material. In glass manufacturing, the cooling rate is often critical to the final product. If molten glass cools too quickly, it cracks or shatters. The last factor is thermal conductivity, or how well a material lets heat move through it. Metals are usually good conductors of heat, while insulators are not. This house is well insulated. The insulation is a poor conductor because it stops the flow of heat out through the walls in winter and inward during the summer. These 4 factors, temperature difference, surface area, thickness, and thermal conductivity, all determine the rate at which heat energy will move in a thermal system. A modern example of all these factors in action at the same time is the space shuttle. When the shuttle is returning from space at 25 times the speed of sound, the friction from the air generates thousands of degrees of heat on the outside of the ship. That's a very large temperature difference between the outside and the inside. At the same time, the surface area, the entire outside skin of the shuttle, is very large. The metal of the skin is very thin and a good conductor. All these factors lead to a situation where a lot of heat outside the spacecraft will move very quickly inside and fry the astronauts. So the outside surface of the shuttle is covered with extremely poor conductors of heat. They're thick enough so any heat which does begin to move through it will take a very long time to make it inside. Virtually all energy we use ends up as heat, and whether we're trying to generate it or trying to get rid of it, knowing the rate at which heat flows will help us control it. When this series began, we looked at force and the things that act like force. We saw how force causes things to move. We saw how force can be a pull or a push. We saw how it can cause an object to change its direction or its shape. Then we looked at work, which measures exactly what force does. We saw that force alone is not enough, that work is only done when something is moved by force. So electric charge is moved by voltage, an object is moved by force, fluids are moved by pressure, and an object is rotated by torque. But remember that time was not part of the work formula. That is, it doesn't matter how long it takes to do work. If the force and the distance are the same, the amount of work is the same. So if you want to measure how much faster one object moves than another, you're measuring rate. So for example, in a mechanical system, you start out with force. Force times distance is work, and distance over time is rate. Rate. It measures how far an object moves over time, how often something happens over time, or how much of something moves over time. The rate at which an object moves from one place to another is its speed. Speed is a unit of distance over a unit of time. In fact, you could think of a speed limit sign as how fast you can move a vehicle, but you could also think of it as a distance that you can drive in 1 hour. If you drive any farther than that, your rate is too fast. We have also seen the difference between a constant rate and a changing rate, or an acceleration. A constant rate covers the same distance for each unit of time. While an acceleration or a deceleration covers a different distance with each unit of time. You can think of an acceleration or a deceleration, starting, stopping, as the rate of change or the rate of a rate. Rotational rates can also be constant or changing. The displacement is still a distance, it's just an angular distance. It's represented by theta and could be measured in degrees, radians, or revolutions. A tachometer is a good example of measuring rotational rate. It counts revolutions per minute. Mechanical rate can also measure an event, or how often something happens over time, such as production rate. When speed is not important, as in the case of fluid, electrical, and thermal systems, rate measures how much moves in a period of time. How much in a fluid system can either be how much mass moves over elapsed time, which is important in cases such as air-to-air refueling, or, as in the case of the power dam, how much volume moves over time. In electrical systems, it's very convenient that the ampere also happens to be a rate, the number of coulombs moving past a point every second. Whether we're trying to generate heat or take it away, it's moved from one place to another in thermal systems. How fast the energy moves, or the rate of heat flow, is not quite as simple because there's 4 conditions. Temperature difference acts like force to actually move the heat. Surface area makes it easier for the heat to transfer. Thickness is how far it has to go. And thermal conductivity is how easily a material lets heat travel through it. These are the conditions that determine how fast the heat moves. But the thermal rate itself is simply the number of calories, or BTUs, that were displaced over a period of time. Controlling rate is an extremely important factor in the operation of technology. We constantly have to be aware of how fast a machine operates. If the rate at which fluids are pumped through pipes is not carefully controlled, turbulence can be created, which can either interfere with the flow or do damage to the pipes. Electrically operated machines not only depend on a steady flow of electricity, but the relationship between electrical rate and heat can spell disaster for equipment and people. Heat can either be a friend or an enemy, depending on what we're trying to do with it. When it's an enemy, it's vitally important to know the rate at which the enemy is moving, so we can keep it at bay. When it's a friend, it's an expensive friend. Heat is a valuable form of energy. It costs a lot to generate heat, and sometimes just as much to remove it.
Batter up.
Just about everything we do involves rate of some kind. How far, how often, how much over time. Take, for example, a baseball game. Now, the ball has to go from the mound to the plate in the shortest possible time.
Strike one.
What? That determines its speed. Then there's how often. For example, how often you swing the bat.
Strike two.
This determines how often you survive in this game. The building itself, the stadium, spends about $8,000 a month on electrical bills, and that's determined by the rate at which electrical charge goes through the lights and all the equipment that operates this place. Then there's the thermal rate, when all the bodies crowd into the stands and they cheer you on to greater heights.
Strike three.
I guess the only thing I haven't mentioned is fluid rate, but this is a dome stadium and it doesn't rain in a dome stadium. Very funny. This program was produced at the facilities of Telemation Productions and is part of Principles of Technology. A project of state and provincial vocational and technical education agencies in association with the Agency for Instructional Technology and the Center for Occupational Research and Development. Together, serving education.